Happy birthday to me. Happy birthday to me. Happy birthday, dear Jason. Happy birthday to me. So yep, welcome to now the birthday special of Algos in 10, season 2, episode 4. We've covered obviously from last episode the really amazing a week away algorithms of Dijkstra, Prims, and Kruskals, and the confusion matrices. Now I'm actually going to show you how it's supposed to be coded, which is pretty awesome. So I'll share my screen. Some topics to go over today. Just a quick quiz about hexadecimal, hint how old I'm going to turn. How old am I going to become? Dijkstra, Prim, Kruskal, APSP, all pair choice path before Warshall, including little diamond programming, review, confusion matrices metrics, and a very short demo of the code, which is like 15 minutes. I know last time the demo went way too long. This time will be way shorter. And finally, episode 5 preview, which is, of course, a very nice topic of ROC, receiver operating characteristics, plus some potential bonus episodes you might be having. So yeah, the quick quiz. What is 0x1a in decimal? I'll give you guys a minute to figure out. Okay, that's time's up. So that's how old I am right now, 26 years old. It's 1 times 16 times 16 to the first power, plus 1 times 10 times 16 to 0 power. 10 plus 16 equals 26. How old I am now. So you can see I am repping my company today, Dell Technologies. Yeah. So at Dell we use a lot of hexadecimals, which is pretty cool. So yeah, that's awesome. We use a lot of hexes at Dell. So yeah, here's the coding solution. So these solutions not exactly of my creation, but because in the real world, the Dijkstra, Kruskal's Prim is extremely difficult to code from scratch. It's just working implementation. For Dijkstra, I basically use like an adjacency matrix. For Prims, I use the min span tree with priority queue. And for Kruskals, I use min span tree with avoiding cycles. And the definition of a cycle is a situation where there's at least a double traversal of any nodes in a complete graph G with V vertices, E edges. And of course, the coding demo also show you an abstract way to like make the adjacency matrix of nodes. So yeah, here's a little spoiled Warshall review. All pair shortest paths. So apply the Floyd Warshall all pair shortest paths APSP to the following graph. It's not related to the episode at all. It's just a nice little review. So like not related to the episode, just a nice simple 4-node graph, easy to like calculate. To have this graph S, A, B, C, and you can see I already done the hard work of initializing this graph. Basically from S to A, the weight is 1, S to C, the weight is 6, S to B, the weight is 2, B to C, the weight is 5, A to B, the weight is 3, and to find the A to C, the weight is 4. So you can see all these values are filled in for like the first iteration of the Floyd-Warshall all pair shortest paths. So generally for Floyd-Warshall, we want to choose the shortest, like the min of like all available paths. And similar to Dijkstra, you want to also might find the most optimal like shortest path. So you can see since each node cannot like connect to itself, we have a row of zeros, and any node is not reachable between. The edge value will be infinity. So I'll give you guys a minute or so to like think about how would you go about Floyd-Warshall. The point of the episode is not to actually apply Floyd-Warshall, so understand like how Floyd-Warshall works, and then like how would you do it in terms of like updating the nodes. So for example, from going from node S to C here, I'll do a little annotation. Draw circle. So going from S to C over here, you can see there's a path of 6, right? But there's a shorter path than 6. There's SA to C with a value of 5. So you always choose the SA to C instead of S to C. This will be very important in a later episode where we talk about Edmund Carson and Ford Fulkerson from the mass flow min cut graphs. But for now, this is all good for general, like right now this is all good for like general purposes of the algorithms. All right, here's the solution. So here's after we have done our d equals 4 graphs. I do this offline, obviously, because it takes a while to figure out Floyd-Warshall. After we apply Floyd-Warshall, we basically get these diagonal zeros again. We get infinity, as I mentioned before. Eventually, you get from B to C, which is a value 5. And then the shortest path from actually S to C after you apply all Floyd-Warshall is 7. So the shortest path in general is from SA to C, which is just a path value of 1, plus 2, which is 3. So that's all you need. Of course, now we get to the confusion matrices, which is another metrics we talk about. And there's a Wikipedia link to look at confusion matrix. So let's take a look at the link. It's really mathy, so don't worry too much about the metrics. The metrics is pretty simple. You know, it talks about condition of true positives and condition of negative, which is true negatives. And you have false positive, false negative. So if you've ever done like some AI or like some machine learning basics, you understand what confusion matrix does. So today we're not going to go too crazy with this stuff. We're just going to go over essentially sensitivity or specificity, precision, recall, those type of things. And maybe just a little bit extra, we'll have the F1 score, which is the harmonic mean of precision and this sensitivity. We're going to use this formula instead to calculate the F1 score. Oh, and also one very good thing, we're not going to do this from manual like last time. We're going to actually use a Python library from sklearn to do the work for us, which is pretty awesome. Yeah, and then also in regards to confusion matrices, we have Numpy usage. This is a very general way to make a Numpy array. Import Numpy as NP, you have array equals a very simple 2, 2, 4, 4 array. So the array very simply, if I were to draw like a table for it, it's just going to be this. Very simple 2 by 2 array. Two, 2, 4. Sorry, 4. And it's a little bit off, but whatever. I'll just make it a little bit neater looking so it's not too off. So here's a quick question. Apply the formula from the bottom, the AD minus BC, to find the determinant of the array. Well, this one's pretty easy. It's going to be basically determinant of 0, 8 minus 8, which is 0. So this particular array, we cannot actually do the operation because we cannot do a Numpy array because it's the determinant of 0. So this code actually will not work, but this is like a general way to like display a Numpy array. Let me get rid of all this. And here is the example I found online from the numpy.org Python library. Also, we cannot do the basic determining thing in regards to rank of 0 either. With the matrix of rank 0, we can also not determine np.array for that. So let me just quick look over NumPy here. As you see, for NumPy, it's a little bit advanced, so I'm going to go through the parameters one by one. So NumPy.array, of course, you first have array, which is an array-like object. You have dtype, the data type of the array. You have copy, which is like basically, if you want to make a copy of the array. You have your order, which is like your memory layout. This is more advanced. I'm not going to worry about that. And then there's an example down here. So you have, for example, np.array 1, 2, 3. That's very simple 1 by 3 array. And something more interesting, which we have done, is the 1, 2, 3, 4. So the determinant for this is negative. It's 4 minus 6, which is minus negative 2. So that means this array is going to be with a negative determinant. And you also could do array np.mat, which is like basically converting it from like an array to from like a subclass of an array to a matrix. Like very basic linear algebra work. So yeah, with that being said, now time to get to the code. So I have the code up here, which is pretty awesome. Yeah, here's the code. So the coding is pretty simple, although it's not exactly all my creation, but I understand most of the code to like explain it to you. So just as a review, it's basically the giveaway Gamber's problem again with the candy bacon, marshmallows, Nutella, Drix cereal, and graham crackers, which actually is not bad for a birthday cake topping, except I want to eat healthier, not eat all these things. So I'm going to just say we enjoy these virtually. So we played basically a little bit of Dijkstra, Prims, and Kruskals. So this we've already gone over how to import network, import like graphs and everything. That's good. This is the abstraction of the graph. Just an extra draw, make an abstract graph. Here's where things get interesting. So the Dijkstra here is different than how I would have done it. I would have actually done the matrices first and then do Dijkstra, but this guy apparently decided to put Dijkstra first. So for the Dijkstra, you basically want to choose the smallest path between any possible paths, and you want to update the node based on like the all unvisited neighbors, and you want to update the distance of a neighbor. The current distance is greater than the distance that's just been calculated, so you want to keep like a loop of update basically for a neighbor index in range number of vertices. This is where it's important. So I basically did this like print statement for basically extra debugging. And as you can see, we calculated from before, the distance of a Dijkstra is 10. So this means that the shortest path distance will be 10 as well. Next up, we have prims. Yes, we have prims. So prims is a little bit different. You have to like first make a min span tree, which if you remember from previous episodes, it's like basically a minimum spanning tree, like the tree that has the minimum weight edge of a graph. And to do that, we have to basically find a min key, like to find the minimum key value. And because I'm using Python 3 and the original code is in Python 2, I had to use a sys.maxsize. I had to import sys, a library for this sys thing from Geeks from the Geeks. I would not recommend doing this if it's like a leak code or actual interview problem. This is just for illustrative purposes. Definitely make your own code when you're actually like doing problem solving. Otherwise, the interviewer will ask you how you understand this stuff. And if you don't understand it, they'll know it's not your code. So be careful with that. But for the purpose of the episode, I basically made it like this. So for prims, you basically do the same thing. You go through every vertex possible in a graph, and you basically make a min span tree set. And for every time you have like vertex smaller than the current min span tree value, you basically update the parent node. So that's what you do here. You get an edge, pairing, and then the weights. And finally, we have Kruskal's algorithm, which is the hardest. You basically want to avoid any cycles. So to avoid cycles, we want to use something called a union find, union find between like basically two sets of vertices X and Y. So if the ranks are same, which means you basically found a cycle, you want to basically increase by 1. And to initiate the graph, you have vertices and graph, which is a default dictionary. You can add edges to your graph. So like for Kruskal, you want to basically build a graph given like different vertices. So as a quick drawing, I'm going to show the following. So for example, this is like 1 graph, 2 graph, 3 graph, 4 graph, 5 graph, 6 graph, right? So for Kruskal, it basically means that you make this dot, you make these 3 lines, make this vertices, make these lines, make this vertice, make this line. Eventually you make like a big spanning tree. And you want to find like the shortest path of all these spanning trees, which is pretty cool. So the main algorithm here is the Kruskal MST algorithm. So you want to like basically keep a track of each parent vertices. You're trying to basically run like an algorithm to check the parent vertices. You want to find the smallest. So you want to first sort all the edges by non-decreasing order of their weight. If you cannot do that, then you can make a copy of a graph, like a residual copy. If then you pick the smallest edge and increment the index for the next iteration. And if this does not cause a cycle, which means if x does not equal y, that's where you have to determine cycle, include it in the result, increment the index of the result for next stage. And this guy forgot a little bit of punctuation. So yeah, we calculated last time for min span tree, the value is going to be 18. So yeah, it's the same thing as before. So note and caveat, as I mentioned before, the coding solutions are just one of many ways to do Dijkstra, Prims, and Kruskals. The general gist of these algorithms is Dijkstra uses the shortest path, Prims use min span tree, and then Kruskal use avoid cycle min span tree. and you basically try to like show this solution. And definitely, if this is lead code assessment, this not be acceptable because it's somebody else's code. So yeah, definitely make your own code when you're like doing this type of stuff. Yeah, like one of the big Dell culture codes is integrity. So be honest with yourself. All right, part B, all pairs shortest paths. So I basically have like a little blurb of how all pairs shortest path would work. We have the problem, like find the shortest path between every pair of vertices of a graph. You have a graph, which definitely doesn't have any negative cycles, or you're gonna have basically not an easy graph to use. But you wanna have like negative edges. And then here's like the base case already written for us. A representation of a weight matrix. So if weight of vertex I vertex j is 0, if I equals j, infinity if there's no edge between ij, and weight ij is the weight of edge. So for example, I'm gonna draw quickly again an example. This is I, this is j, yeah. So this is vertex I, this is vertex j. And I think the colors are a little bit off. So I'm gonna just make the colors a little easier to read. I don't like using colors that are like really, really off. So I'm gonna use dark green to I'm gonna use the dark green color. Oh, sorry, I was just text for dark green, that's all, yeah. Turn that dark green. Yeah, so that's a little bit easier to read. Turn that to dark green as well. So I and j. So the first base case is very simple. If you have an edge between the two, you obviously have, you have basically one node on top of another. It's gonna be 0. If it's gonna be cannot connect the two nodes I and j, it's gonna be 0, no edge. And then we try to basically optimize it. So guess what happens again? I'll first clear all drawings. Yep, the DP, dynamic programming. So we have to yet to do another DP, which is why I give a heads up. You have to review DP to understand this APSP back in episode 3 for a reason. So it's pretty simple. English description, we find the shortest path G of I from all set of paths n where I less than or equal to n. The subproblem is pretty simple. It's one of n possible paths. The development got a little bit hard because they had to worry about like directions of each path. So the base cases are pretty simple. It's basically the same as we just saw above over here, except I added one more thing. If you have something called a Bellman-Ford algorithm, which is like a more advanced form of all pair shortest paths Ford-Marshall, they can allow negative edge weights. Right now, we're not going to because I don't want to complicate this thing. And recursive cases is pretty simple. Either you choose the weight edge you have, or you added an intermediary node k to like determine a shorter path than the other two. And the subproblem is runtime of Oj. I have to make that a little bit clearer, sorry. Oi times j. Since we have to like traverse all the pairs of the shortest paths between I comma j. Find a runtime, yeah, this is good. Basically I times j times n, which is O n cubed is cubic. And then find solution is basically find all the minimum paths of all n shortest paths. All pairs shortest paths coding solution, pretty simple. You have 2, 3, 4 loops. So it's O n cubed, cubic. And basically what we want to do is like update the min as shown in dynamic programming. And this we show a matrix of all the shortest paths with like basically all the graph nodes that we have shown in the previous episode. Finally, we get back to the good parts, confusion matrices. So before I continue, do you guys know anything about true positive, true negative, false positive, and false negative? So on this matrix here, what are the values? We have false and false, that's true negative. And you have true and true, that's true positive. And you have false and true, which is false negative. And then true and false, which is false positive. So yep, there we go. So yeah, for this one, I had to import a few metrics from sklearn, which is a great Python library for it's actually calculating the confusion matrices. I calculate the accuracy score, recall score, precision, F1 score, and just make this even cooler because I use this a lot in my data science course at Northeastern. the classification report. Very good for data science work. This, I really had a long time generating exactly this matrix value by like a bunch of ones and zeros. So essentially, I'm trying to basically make a convolution of like ones and zeros to make the matrix I have up here down here. And then finally, calculated metrics is super simple. So essentially, I keep 4 counters of true positive, false positive, true negative, false negative. And for each one, I just keep on adding. That's essentially, it's just like 4 times accumulator. And then in the end, I basically make a bunch of helper functions to run this thing. And this time, every time we run, we'll get slightly off in terms of accuracy because of running in terms of significant digit errors. There might be a little bit of a rounding error here, as I mentioned down here. So now I'm gonna run all the code at once to show you how it works, and then we'll move on to the episode. So yeah, this is a way shorter demo than episode 2 because I noticed I talked way too long for like the pedantic graph parts. So I'm gonna make it a lot shorter today, just to make it sweeter, and of course, continue enjoying my birthday as well. That's also a good reason. So yeah, I make another graph. Dijkstra looking good. Yeah, Prim's looking good. Kruskal looking good. All pair choice paths looking quite nice. No change here. This the same. Yeah, you can see there's a little bit of variation now with the accuracy and precision. It used to be like 0.62, now it's like 0.63. That's okay, as long as like within 2 or 3 sig figs, you'll be fine. If it's like 0.62, 0.7 though, you have something wrong with your confusion matrix accuracy. And in the next episode for episode 5 with ROC, the receiver operating characteristic, we're going to show you how those types of inaccuracies could cause a problem with regards to building your ROC curve. So yep, that's the demo of the curve. So yeah, there's episode 5. So episode 5 is pretty straightforward. You have essentially ROC curves and SciPy, and it's sort of a Marvin API character. If you read Chinese, you know who I'm talking about. Do not worry, there's no, I know this looks crazy, right? Some integrals and calculus and crap. You don't have to worry about that. All you have to worry is this thing over here. So you basically have to worry about the ROC curve, the true positive rate, and a false positive rate, and it's been called the AUC, area under the curve. You want to avoid having a curve that's a straight up like y equals x line. That's like basically random guessing, 0.5% probability accuracy. You want to have a nice like hyperbolic or hyperbolic curve over here, relatively symmetric. And if it's all up here, it's almost like a perfect match. You basically have everything true positive, everything false positive. That you can do with like something called gradient boosting and some more advanced algorithms. But for this one, we're using something very simple called a decision tree classification algorithm. So yeah, that's it for episode 5 preview. And now there's a little referendum or voting chance for you guys, the audience. As the summer winds down, I was just thinking about what should I do for a bonus episode. So I do have a few Northeastern friends I could do a guest collab with, like do a little data science algorithms review. I could do something called a logic puzzle, like a zebra puzzle, which is pretty cool. Something I do for my just keep your brain fresh and like understand stuff. Any other topic that's at least reasonable I could cover? Or do you think, oh my God, this is just too much Jason during the summer? 10's enough. So yeah, just vote in the comments or like vote however you want. And the results of all the voting will be shown in episode 5. And yeah, the summer is flying by fast. Just one more month, guys. Okay, that's it. So yep, see you guys in probably 2 or more weeks for episode 5, season 2. And of course, this thing is the best thing ever. Yes, thank you very much, Bailey Madison and Kevin Quinn. Yep, and make sure to like and subscribe. So have a good day, guys. And of course, I'll keep enjoying my birthday and hashtag algorithms.